Hello, hello, hello! Welcome back. What day is this? It is Thursday, the 1st of April, and today we are going through gas laws. Different setup. I'm in a stead position. It's Easter, which means that I am just super busy, and I'm like, all right, if I sit down for like 8 hours a day, I will go clinically insane. Apologies if there was if you were sort of put off by all of that laughing at the beginning, but there was someone in chat who was like, hello, 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 and I was like, you know what's up. You know what's coming. Welcome. I genuinely wonder at what point am I going to change that intro, but hey, here we are. Hope you guys are having a good Easter. Because I know as soon as I hit April, I'm like, oh, okay, you can feel it now. It's on the horizon. This is where I've stopped teaching people, and we start getting into all the exam technique, and I step back a bit, and I'm like, do a paper. Just do a paper. Let me watch you do a paper. Oh, no, not that, not that. And I kind of really hand it off to the students. So I'm hoping you guys kind of feel that same sort of like weight on your shoulders, like, all right, here's how it feels. This is going well. This isn't going well. And kind of getting into the vibe of it. I think as well, getting enough rest that you can kind of hit exam season, sort of like up and running at full speed, great. But also not taking so much rest that you kind of go back and it's like, wait, I haven't done any work. So finding that balance for you, whatever that means for you. So today, gas laws. I even, by the way, might go, there's a non-zero chance I go live tomorrow or Friday with a live solve of a math paper, by the way. So I'm going to take my time at the start here, kind of wait for people to sort of slowly drip in. If you're going to drip in, I will say it was very funny because if you're now not in the Discord server, you're officially missing out. Because I was very, very proud of myself. When I announced that I was going to be doing the stream, I put in the little announcements. I was like, try to make it, but if not, no pressure. And I was like, pun, 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 pun. And then someone tried to pun back and I went, no, not today. And I sent him right back. It's like, your pun game is related to gas laws, absolute zero. And I was like, boom. Apologies if you took that personally. It was not intended personally, but also if you tee up an opportunity like that, I'm gonna take it, right? That's just non-negotiable. I'll apologize afterwards, but I'm gonna take the opportunity. And I kind of like that. I kind of like that there's a bit sort of back and forth and banter in the sort of Discord now, giving it a little bit of life. So we'll see. We'll see if I can come up with clever puns for any sort of future physics streams. Our live chat has doubled to 2. And with that, I think we can launch into... I'll put you guys over there. Let's get the whiteboard started. Also, as always, feel free to drop things in the chat if you have specific questions pertaining to gas laws. Plan is to do gas laws and kinetic theory, including that monstrous proof, that monstrous derivation of the kinetic theory stuff. Because I remember I was teaching it to a student once. I went, don't bother. There's no way. There's no way you'll ever need to know this. Come to the exam. What's on the exam? That derivation. I'm like, oh, God. So, yeah, we're going to have to go through that derivation. I'm going to be textbook supported. I'll have a little bit on the side as well. But I say, let me just get into it, because if I take my sweet time, we're going to be here all day. But I don't have someone after us this time, so I can theoretically go over if I need to go over by like 5-10 minutes. So, massive stream of consciousness out of the way. Gas laws. First things first, what are the gas laws? 3 theoretical gas laws. We have Boyle's law. Do I want this to be a little bit thicker? Maybe I want to zoom in more for that, because I like how in the sort of presentation on that is not how you erase. We are professionals here. We are good at our jobs. We do live streaming well. If I zoom in a little bit, maybe that'll make it a bit thicker and a bit clearer. Good enough. So we have Boyle's law. We have Charles's law, and we have the pressure law. And pressure. So Boyle's law says that PV equals constant, which is the same thing as saying P1V1 equals P2V2. Oh, watch all your interview prep streams. Oh, congratulations. You got an Oxford physics offer. You are very, very welcome, sir. impossible to get an offer if you don't deserve it. So all on you. So here, now it's just a case of making sure you meet that offer. So like, because it does happen. It does happen. Don't be the one. Get yourself good and ready. So Charles's law says that volume is proportional to temperature, which means that so V over T equals a constant, which is the same thing as saying V1 over T1 equals V2 over T2. Come on, you can do it. The tech is teching. Right, so pressure law says that pressure is proportional to temperature, which is the same thing as saying P1 over T1 equals P2 over T2. Now, these forms underneath are ones that are much very helpful for things like what I call before and after cases. So they give you the initial case. They're like, all right, now what about when like the temperature's doubled and the pressure's tripled, and like what happens? That happens especially in like multiple choice or IB stuff. So if that's the situation, getting used to this form, super handy. Also super handy is knowing what to expect in your graphs. So this would be an inverse relationship for pressure versus volume, because pressure is inversely proportional to the volume. Down here, we're going to have that volume and pressure are both directly proportional to temperature as long as the temperature is in Kelvin. They are so sneaky in this topic about units for temperature, and do not be the one to fall for it. It's so easy to get confused between the Celsius and the Kelvin of it all. So directly proportional, as you know, straight line through the origin. Now, this idea of Kelvin and absolute zero is something you need to consider. So absolute zero, as you hopefully know, comes from the idea of doing sort of pressure or volume against temperature. Read my mind. What would be the Celsius graph? What it would be is something like this. And in fact, that's what they did experimentally. So they track it back to about 0 degrees C. You get the temperature, the pressure over a range of realistic temperatures. And what you find is it's linear and would track back to a pressure of 0 at some value by linear extrapolation. And we find that that is minus 273 degrees C. It's 0.15 or point some other stuff. But the point is, by tracking back the pressure temperature curve in Celsius, where it hits the x-axis, that is absolute zero. That's how we came up with the idea of absolute zero. And we defined that as 0 Kelvin, where 1 Kelvin increase is the same as 1 degree C increase. So that's where it comes from, the pressure or the volume curve against temperature. So just, yeah, it would just be, so also, if you know from, typically, if you're doing physics, you're doing math, so you could just consider this a graph transformation, f of x plus 273. It kind of shifts it left or right, depending on which curve you're talking about. Just a bit of a sort of tie in there. So that's important to know where it comes from. What else matters? So what else matters is we can combine all three of those experimental gas laws into a single gas law, which is the ideal gas equation, PV equals nRT, which, by the way, you can also say PV over T equals constant, which means that P1 V1 over T1 equals P2 V2 over T2. This is a form you see sometimes in the IB, and if there's sort of changing all three at the same time, you can just use this for quick comparison rather than going through and working out what that constant is. While we're here, we should also discuss what assumptions must be met in order to make these true. So for instance, we've said PV over T is a constant, but that's only going to be true when nR is a constant. Now, R is just a constant. It's 8.3145. It's the gas constant. But N does not necessarily have to be a constant. N is the number of moles of gas. So if the number of moles of gas were to ever change, that would change the constant, and this relationship would now not be true. So that relies on, for instance, a closed system. So that's necessary for this thing to be true. And we can also consider it for these other laws. So here, PV equals constant. When is that true? That's true for a constant number of moles, so a closed system, but it's also true for constant temperature. So I'll kind of put these, so the closed system is universal for these, but this assumes constant temperature. Charles's law assumes constant pressure. And the pressure law assumes constant volume. Can I? Yeah, I can spell. Oh, good. Go me. Okay. So understanding what must be in play for these things to be true can be very important, because this can help you understand how to set up an experiment to test these relationships. Right. What else is true? Well, there's the counterpart of this, which is PV equals NKT. Some people bother with the KB. I don't like it. I'm going to just call it K. But the thing here is that you have one form when you're dealing with moles, and you have another form when you're dealing with number of particles. So there's the particle relationship, and there's the mole relationship. But the PV over T equals constant would still hold regardless of which one you're working in. Someone is attempting to pun. Outrageous behavior. So, are we going to be talking about molar mass? Ooh, Vivan, I remember you in the chat. I'm thinking of applying to American universities as well for engineering. What are your thoughts on getting an undergraduate engineering degree from Oxbridge Imperial versus the top US universities? Well, okay, I'm going to stop just to have that conversation. So when it comes to universities, especially the US system, it's it's longer, and the reason why is because you go through like a more liberal arts system. So if you were going to like Oxbridge Imperial, you would go in and you would study engineering and nothing but engineering, whereas in a US system, you would be studying like everything. You would do a sort of mix. It would almost be like doing the IB for like the first year, and then you're allowed to specialize as you move through. So the minimum a degree takes in the US is 4 years, and then 5+ if you wanted to go on to masters, whereas in the UK, normal undergrad degree would be 3 years, and then you would get the master's after like a 4th year. So it would be faster and more specialized. Another thing to note is if you were going to the US, you would be probably applying as an international student and therefore not be available. You would have to look into this. I'm not sure how scholarships would work, but typically international students are paying like full fees. So financially, I know American universities are extremely expensive, especially those at the top. So that's another thing to be very, very careful of. Personally, the reason why I didn't apply to the US, even though I was a citizen, is because I knew I was just used to the UK system. Like I was adapted for it. I was doing A-levels. They were all math and science-y based. I didn't want to have to go through the SAT, which I knew people were going to be prepped on for ages with like essay components and English language stuff. And I just kind of went, all right, I know the system I'm in. I knew I wanted to do science, and so I could specialize right away. And it just sort of suited me better from that perspective. But if you feel like you want to sort of dabble in some other things first and then specialize in engineering, maybe the US would be for you. So just something to consider. Yes, gas laws. I mean, granted, you joined just at the point that I was talking about anything but gas laws, but yes, back to gas laws. So we've considered this stuff. We've got our ideal gas equation, PV equals nRT. Cool. So is there anything I need to consider here? Not yet. We are going to, when we get into like the kinetic theory stuff and we start bringing density in, then that's going to matter. But for the whole, this is completely fine. Okay, so do we need to, let me just check if we need to do anything else with that, or if we can go straight into kinetic theory from here. Some syllabuses I see require work done by a gas and the first law of thermodynamics. So let me make sure I cover that while we're here. Or rather, okay. So I'm just going to try and give, if this isn't on your syllabus, please bear with. It's on some syllabuses though. So if we have a situation where we have a piston, say, Question in the chat. How do you recommend to remember the names of laws and equations for this topic? It seems so similar. Do you recommend using dimensional analysis? The names I care about less than the equations. And then if you remember the fact that they all just come from the ideal gas equation, PV equals nRT, then I think you're kind of going to be fine. For me, I just know Boyle's law because Boyle's law I've known forever. That's the one you get introduced to. Pressure laws, then there's the other two are like with T. The pressure law is with pressure, and then the only one left is Charles's law, which must be V and T. So that's how I remember the names. And then on the whole, I just remember like the relationships. So we'll get into that when I kind of, but if we're talking about a piston, so let's say, oh, nope, nope. I'm so bad at tech, guys. All right, so let's say we have a piston, and let's say the piston is moving out under the action of the gas in here. Then if that piston gets moved to here, what happens is there is a change in volume. And the work done by the gas to push the piston out is given by the equation work done equals pressure times the change in volume that you see. So that may be relevant to you. It may also be relevant to you to consider that the internal energy. So if you're supplying heat, I want to be really careful about this. So Q equals delta U. I'm going to say minus W, but let's think about what this means. Q, so this is the first law of thermodynamics. I think I've covered this before on the channel. So this would be heat supplied. No, honestly, come and ask questions. Do not worry about asking a question. That's what I'm here to do. This is the increase in internal energy, which is due to it raising temperature. And this I got to be really careful about. So you supply heat, some of it goes into, so the internal energy increases, and this would be work done on the system, I think. I can never remember if it's work done on or by. So let me derive this. So if you supply heat, yeah, I think it would be plus if it was work done on the gas. I think it's negative if it's by the gas. Okay. And the way I think about this is like, if I'm supplying the energy, no, it's on. In this variation, it's on. Here's why it's on. Because you can consider the reverse of this and say delta U equals Q plus W. And it's clear that the way to increase the internal energy, you could supply it with heat, but you could also do work on it, which is, okay, so that makes more sense to me. How do I increase the internal energy? By supplying heat or doing work on it, which means in this form, this is work done on the gas. If it was work done by the gas, that would be positive. I always struggle with that, so hopefully this helps you struggle less with it on your end. Okay. So, yep, that is thermodynamics if you need it. Just checking quickly if anything else is required. Not really. I'll leave the required practicals to you because they might differ sort of syllabus to syllabus. But let's get into the kinetic theory. First things first that I haven't said while we're here, I have said that delta U is the internal energy, but I also said that means that relates to the temperature. Well, why does that relate to the temperature? What is internal energy? We covered that when we were doing the heat stuff, right? So we said that the internal energy was the sum of the kinetic and the potential energies of the various particles. Now, we said that the potential energy was raised by changing state, and the kinetic energy was raised by increasing the temperature, because temperature is a measure of the average kinetic energy of the particles. That causes a bit of a problem because when we're talking about ideal gases for the ideal gas equation, we know that ideal gases follow certain assumptions. And these assumptions are super, super important and vary slightly in their wording, syllabus to syllabus. So know your wording. But let me just outline some of what I think are the most important gas laws. Not the gas laws, but the assumptions, right? I'll just be supported here to make sure I don't miss anything. One of the most important is, so ideal gas assumptions. Oh, no, that did not mean to be an exclamation point. So ideal gas assumptions, first one that I think you guys really need to focus on is the fact that they exert no forces on each other except for collisions. So they do not interact, exert no so they exert no forces on each other between collisions. That's one form of it. Or we can say that they don't interact, or we can say they have no potential energy, which was kind of the problem from earlier. We said that in order to become a gas in the first place, we have to raise the potential energy. And then we say an ideal gas, yes, this is talking about the particles. Now we're saying ideal gas has no potential energy. And that the only thing that contributes to internal energy is the kinetic energy. But that is an important assumption. Another important assumption, the time between collisions, or rather time of collisions, is negligible compared to time between collisions. Don't you just love big, dense writing? Love it. So accessible. So negligible compared to time of collision. Sorry, time between collisions. What am I saying? No, time, but guys, I swear I'm literate. I keep on. Do you know what? I may not be able to prove it to you, but I promise you I am. So the consequence of this first one is no potential energy. What's the consequence of this second one? What must be true to be an ideal gas? Well, if the time between collisions is negligible, sorry, if there's, what it means is that there's a very long time between collisions, which means they're not colliding that often, which means low pressure, low temperature, but especially low temperature, because if they had a high temperature, they'd be zipping around and colliding all the time. So you favor ideal gas behavior at low temperatures. Oh, did I miss a message? Apologies. Whoop. Left a follow-up question above. Sorry, apologies. I did miss this. On the same note, do you know? Let's pause a little bit to answer a comment question. So, on the same note, do you know what the job market and career potentials are like for US versus UK? Does either favor engineering more? That is beyond me. I think, well, I mean, everyone favors engineering, but also engineering, you don't have to go into engineering, right? So a lot of engineers might go into like patent law, which would be the same in the UK and the US, because you need to be able to understand the inventions in order to understand what you're allowed to patent and sort of argue whether something is a true novel invention. So that's one thing that a lot of material scientists and engineers get recruited for that. In fact, you must be a scientist in order to be a patent attorney. Obviously, there's straight engineering jobs that you can be had. You prove that you're numeric. You're not going to struggle. With an engineering degree, you're not struggling for jobs anywhere. So I honestly, I wouldn't think that would be the deal breaker in terms of your decision. I do think salaries in general are bigger in the US, but that doesn't mean that you have to get a US degree to get a US job. It's perfectly okay to get a UK degree and then transfer over, especially if it's like a degree like Imperial or like Oxford or something that they know. It's not that they're going to be like, oh, who is this guy from the UK from a degree that like a university that I've never heard of? Like, it's engineering. You're going to be fine. um, what type of engineering matters as well? I suppose that matters. That does track. Um, but also, I think I don't know if that's something that's really important to your decision. Seek further advice outside of me. From my perspective and where I stand, I don't think that would make the biggest difference in your choice. Which is why if it would, then seek other advice. Okay. Right. How is a math and physics degree for jobs? Similarly, you're gonna be fine. Like you were gonna be just fine. For me, having a science degree from Cambridge, I was just like, I'd like to do your thing, and they went, yes, and I'm like, is your thing relevant? They're like, I don't care. So you're gonna be fine. Right, back to streaming because I think this is not when we talk about the assumptions. Not often do people talk about like the implications of these assumptions. So it's kind of done implicitly, but not like properly. So the fact that these things don't exert forces on each other between collisions, that means no potential energy. The time between collisions being big compared to the time of the collision means low temperature. This is one where you can get these wordier questions. What I recommend for wordy questions, by the way, mark scheme analysis. If you see something, then you see how it's been laid out in a 6 marker. You just memorize that 6 marker and give it back to them when they ask it again. So the other really important one is that the volume of an particle is negligible compared to the volume of the container. Now, this has an important consequence, which is that the pressure must be low. Because if there's a high pressure and they're packed together, then first of all, they are also colliding more frequently, which hits on assumption 2, but it also means they're packed closely together and they start to like have non-negligible volume, which becomes a problem. So ideal gases are favored by low temperatures and low pressures. That's when they behave most ideally and are most likely to be accurately predicted by ideal gas equations. You will notice that there are certain applications where we kind of need to know how the gas will behave, which do not follow low temperature and pressure, like engines, and I will say no more on that. But these are my main 3. I'm going to quickly go through and see if any are particularly important. So like elastic collisions is an important one. I'll add that. So all collisions are elastic. And sometimes, depending on your syllabus, they could include other things like they move in straight lines between collisions, which is kind of a consequence of this first one because there's no forces deflecting that motion. Molecules. Sometimes you see that the motion, the potential and kinetic energies are randomly distributed. That depends on your syllabus. You can molecules can be considered perfectly elastic spheres. I know it's like continuous random motion. Newton's laws apply. Very large number of molecules. These are more of the sort of round the outside assumptions. I think these are the main 4 that, like, if you know these, you're going to be fine. Now it is time. So let's talk about where the kinetic theory equation comes from, because this derivation is just so evil. So first, okay, let me talk about what I'm talking about. Where are we trying to get to here? We're trying to get to the point that PV is a third nm CRMS squared. Now, this derivation is just, Oh, another thing which confuses me is the Maxwell Boltzmann distribution is not really taught rigorously. Not if you're not a chemist, no. But we may as well as long as we're here. Because also, I'd rather just do this next bit in one chunk because that's going to. So the Maxwell Boltzmann distribution tells us about the number of particles that have a given energy. There are no particles with no energy. It quickly rises to a peak and then it kind of goes down like this. So there are very few particles that have extremely high energy, and there's a maximum amount of energy which is determined by the temperature. The average kinetic energy, as we say, is a measure of the average. The temperature is a measure of the average kinetic energy. Now, what happens is if you increase the temperature, the peak happens later. So the peak happens at a higher energy, but you see that there's this kind of, it sort of flattens and moves to the right. So on the right-hand side, it is sort of above the curve at all high energies, but it's below the old curve at all the low energies. It does get wider. But what we find, though, is this is, by the way, important to note that it's not often talked about, but the number of particles equals the area under the curve. So if it's the same gas being heated up, the total area under the curve should be the same. And because it dies off exponentially, it will converge as you integrate up to infinity. So this sort of area on the left here should equal this area on the right here. So yeah, total number of particles equals area under curve. Okay, they just move around in terms of their energies. This is used more often in chemistry than in physics, but it could be relevant to you. So yeah. Oh, it's right here, actually, on the distribution of speeds. Now, let's talk about where we're going to get to with this kinetic model. So we're going to get to the point, that PV is a third nm CRMS squared, where this is considering particles, not moles. So this is the number of particles. M is the mass of a particle. And CRMS is the root mean squared speed. Now, the reason why we have to do a root mean squared is because if we took the average velocity, that would be 0. It's a vector which considers direction, and the average, it would average to 0 because the gas stays in place. Now, the root mean squared speed, oh, it's so bad, this derivation. The root mean squared speed is a way to measure the average speed rather than the average velocity. So you square everything up to get rid of the signs so that regardless of whether it's positive or negative, the square is the same. You then take the average of that square and then square root it back down to get a sort of measure of the average speed of a particle. And that's kind of how to think about it. Now, where this comes from, and again, I have seen this come up in an exam, knowing how to do this, where I'll first clarify the derivation. So in other words, the CRMS is equal to the square root of, you sum up all the individual squares of all of the individual speeds, and then you divide by the total number of particles. So it's the squares, you mean them by summing them up and dividing by n, and then you square root that whole thing. Now, let's walk you through this. So here's what you got to know. We have a box. Okay. So we have the length of the box, which we will call, so this will be the length x, this will be length y, and this will be length z. So what we're going to have to do, first of all, let's take, given that a particle can travel in 3D, let's say it has, let's call it a vector. So let's say the c for a particular thing, for a particular particle 1 will be given by u1 And also, yes, I am being very textbook assisted here because I do not want to go wrong. What this means is that the speed of this particle will be given by, we sort of just do Pythagoras, it will be u1 squared plus v1 squared plus w1 squared. That is the speed of any particular particle with a given 3D vector velocity. No, sir, I have not derived the equation for Wheatstone Bridge. So, what we say now is we consider the time between successive impacts on a given face. So let's consider this front face. So what's going to happen is the particle is going to travel back and forth and hit the back wall and then the front wall. So what we're considering there is the y component. Why do the y component? Let's do the x component. So let's consider instead it is moving, bouncing off these two walls. So what's going to happen is it will travel. So the total distance to get to the opposite face and back is given by 2L. And we know, so it's the time between successive collisions on a single wall. So if we consider it's just collided with the left wall, how long until it collides with that left wall again? Well, it has to travel 2Lx will equal the horizontal speed, which I called u, for a given particle 1, times the time taken between successive collisions with that one wall. So the time between successive collisions with that one wall will be given by this expression. Now, when it collides with that wall, it exerts a force on that wall. By the way, let's talk about that. Why does that happen? Because they like to ask this. The sixth sort of deep dive version of this. Particle collides with the wall. The particle experiences a change in momentum. That means the particle experiences a force from the wall. And by Newton's third law, that means the particle also exerts a force back on the wall. The sum of those forces divided by the area gives you the pressure. That is why gases exert a pressure. When you raise the temperature, they are moving more quickly, which means more frequent collisions with the wall. And it means that each collision is more forceful because the change in momentum is higher, so the force increases, so the pressure increases. Yeah. Now, so that is the time between successive collisions. Now let's calculate that force, right? So the force is the rate of change of momentum. So it was coming in. So let's say right is positive, right? So it was coming in. So the force is rate of change of momentum. The change in momentum is after minus before. So the after, it's traveling to the right. So after, it has the mass of the particle times u1 minus, and where it was before, which is minus mu. Oh, why am I doing this? Equals minus mu1. All over that time. So it's 2mu1 all over the time t. But we know that time t is this. So that becomes 2mu1 times u1 over 2lx, cancels. So it equals mu1 squared all over lx. That is the force on the particle, which means the force on the wall is minus mu squared over L. In other words, acting to the left, which we expect. We expect the gas to be pushing leftwards on that wall. And what we can do is to say that pressure is force over area. So I'll call it positive to not take into account the sign of it, which really is just about the direction. But the force is mu1 squared all over Lx. And this is divided by the area of that face, which is Ly Lz. So we're dividing by Ly Lz. And yes, I do say Lz, and you can't stop me. And that is therefore over the volume of this little cube. So that is the pressure on one face. So the total pressure is the sum of those individual pressures. And that is only the pressure exerted by one particle. So what we can say is that the total pressure on the wall would be given by the sum, using sigma notation, of the UNs squared over V's. So in other words, it's M over V into U squared for particle 1, U squared for particle 2, all the way up to U squared for particle N. So in other words, we can say that there is an average U in the x direction which I will call U bar, multiplied by the number of particles. And that is going to be the pressure from the x direction. Now that is the pressure on that wall. But that is only considering one of the directions. Yes, we are assuming monoatomic. Yeah, honestly, it's the most atrocious derivation. And the fact that it came up in an exam, I was just horrified. So that is now just considering it in the x direction. But now we need to consider the fact that the velocities have components in the y and the z directions as well. So what we find is, given that there's no preference, we could also have said that pressure is mnv dash squared all over big V. And we could have said pressure is, we could have done it in respect to, so we did it UV and W, I believe. All over V. And so if we're going to take an average of those three, therefore, because we're sort of averaging it over the sort of three distances, different directions, we would say that the average would be add them all up and divide by 3. So therefore, add them up and divide by 3, you would get a third m n over v times the average x speed plus the average y speed plus the average z speed, which is just root mean squared. So in multiplying both sides by v, you get PV is a third nm root mean squared speed. That was bad. I hate it. I hate it. I hate that I have to know it. I hate that you have to know it. That's why I have this thing on the side. I don't want to learn it. It's bad. But to recap, what you need to do is to work out the pressure on a wall. Work out the pressure, you need the force times the area. Force divided by area. To work out the force, you need the rate of change of momentum. So you need to work out the change in momentum, which is simple enough. And you need to work out the time between collisions, which is simple enough. So working out the force isn't too bad. And then dividing by the area isn't too bad and turns the bottom into a volume. What we then do is we do that for all the particles in one direction. And then we split that out into the 3 directions and divide by 3 to take the average, basically. And then you get this root mean squared speed. Now, considering the kinetic energy, the mean kinetic energy of a particle is, so the mean kinetic energy would be a half m CRMS squared, half mv squared for the average speed, right? So you'll notice how close that is to this. And what we do, by the way, is we also say that the average kinetic energy of a particle is 3/2 kT. The reason why, well, let's talk about that. So what that means, therefore, if we were to sort of plug that in, 2ek, twice the mean kinetic energy is mcRMS squared. And we can plug that in here, right? So we can say that PV is a third times n times m, times that mean twice the mean kinetic energy. But we know that PV equals n kT. So the n's would cancel. And the average kinetic energy of a particle would be equal to 3/2 kT. Which says what we said it always said, which is that the average kinetic energy, the temperature is a measure of the average kinetic energy of a particle. And then to get the total internal energy, you would multiply that by the number of particles, which would be the internal energy. So it'd be 3/2 n kT, or we would say it's 3/2 nRT if we want to work in moles instead. So that, I hope you will agree, is atrocious. And I'm not even done, because there's also one to do with density that I haven't considered yet. Where is that? Let me just make sure I've got that for you guys. Where is the one that has to do with density? Apologies, let me find that real quick. Physics, I'm sure I'll find it. Yeah, Excel's got some weird stuff. I just can't remember it off the top of my head. It's quite similar. Feel free to ask questions in the chat if you want me to find answers to those as well. I thought it was in here. It's all right, I can edit this out. Maybe go to the higher level. I'm sure it should be in there. So then we find a formula book. I am determined to get this to you. Not I can try and derive it, but I really don't want to. Gas laws. Yeah, this one. So we finally want to get to the point where if we start from this start point, where we have PV is a third nm CRMS squared, we can say that the pressure is a third times nm/v times CRMS squared. Which matters because if we think about what this term in the middle means, that is the mass of a particle times the number of particles. So that is total mass divided by the total volume. And we know that mass over volume is density. So we know that the pressure is also related to the density. So, and the only thing that affects the mean squared speed is the temperature, as we saw up here. So the mass of a particle is the same. So the average kinetic energy, which deals with the temperature. So the only thing that the mean squared speed depends on is the temperature, right? So for a given fixed temperature, therefore you have a fixed speed, the pressure is proportional to the density of the gas, which is another very important relationship. So for fixed time. And that, I think, is the last of the important equations that you need to know. So that is, and you can quote me on this, monstrous. I really don't like the kinetic theory as much as I like the gas laws. Gas laws, fine. Kinetic theory, less fine. But let me see if I can get some... Actually, let's see if I can... The questions in here aren't great. I'll see if I can find... If I think that I'm going to quickly scan this and see if there are any good ones. And if not, we can sort of end early. But, because I think in terms of the theory, that is the theory explained. Obviously, if you have particular questions in the chat, happy to answer those. One thing I think I'll also do... now, lost that train of thought entirely. So, you see, this is what happens when I've been teaching from 9 a.m. But it's all right. I still got to come on for you guys. So, gas laws... See if there are any difficult ones. Number of gas particles present. No, I think it's going to take me a while before I find something that's really good. What would be good, actually, is if you guys could use any past paper questions. That's what I'm thinking. What would be really good, by the way, especially as you're moving through exams. In fact, let's start a conversation. As you guys are moving through exam season, it would be really helpful if you come across really ugly questions, feel free to like take a screenshot and dump it in the Discord server, because I think having a sort of evil past paper question bank would be a really helpful thing to build up. And you guys know more than I do at this point what is going to be really like stressful for you to handle. So for instance, when I was doing my live solve of the 2023 paper 1, and I was like, oh guys, this is so easy. This is so easy. And then there was a question 15 right at the end that was just evil. Definitely dump them, right? And we can kind of collectively build up a sort of an oh my god question bank. And I'm thinking some of these gas laws and kinetic theory things could be part of that, especially like, oh, there was absolutely something I wanted to say. So for instance, I was going through some questions with someone recently, and there was a problem with, so you see it sometimes in the IB where like there's like a big thing and then there's like a connecting tube, and yeah, I'm not going to draw this because internet, but basically there's like one big vessel and then connected by a thin connecting tube and then a smaller vessel, and it's getting, because obviously then and they're held at different temperatures, so the volumes are different, the temperatures are different, but the fact that they're connected means that the pressures must be the same. So if gas can flow freely from one place to another, it will reach equilibrium pressure. So for instance, I had this as well with a student doing a question about a hot air balloon. So there was a big hot air balloon which was open at the bottom, and because it was open at the bottom, the pressure inside the balloon had to equal the pressure outside the balloon. So just bear that in mind. If you're comparing two things and there's gas exchanges allowed to happen, the pressures will be the same in both. So things like that, little tips and tricks that might help you unlock these questions, those will come out of the woodwork as we start to compile more of these questions and I give you guys these solutions. So at a risk of finding you questions that just like aren't great at this time, I think I'll leave it there, mainly as well because I think some of the good ones I've seen are in IB, and I know IB are like bad when it comes to like disseminating their stuff. Yeah, that's what I mean. So someone says like the OCR has one question that mixes this with the Archimedes principle. Like I saw a question on Save My Exams that like that hot air balloon question where it asks you to explain how a hot air balloon works. And the basic idea was you increase the temperature in the hot air balloon, which means that because the pressure has to stay the same as the atmospheric pressure, the volume must increase. Because the volume increases, the density decreases, which means it floats. The upthrust becomes bigger than the weight, and eventually that happens until it starts to float. as you move up, the atmospheric pressure decreases, or it was, and then it was saying it expands more. Like eventually, yeah, the atmospheric pressure decreased, which means the pressure in the inside decreased. But because PV equals nRT and the temperature was constant and N was constant, that means the volume had to increase, so it got bigger still, which means it got less dense still, so it kept on rising. But that happened until the hot air balloon's density was equal to the density of the air outside it, at which case it stops rising. Like, it was a wild question, and it all hinged on the fact that the hot air balloon was open at the bottom, which means the gas exchange can happen, which means that the internal pressure has to equal the atmospheric pressure. Like, it was just insane. So, well, the temperature decreases outside, but the temperature inside the hot air balloon is determined by the heating thing, like the sort of blowtorchy thing that you put inside a hot air balloon. So yeah, like that was wild. Things like that. And what we can do is if we start to gather all of these really ugly questions, I can just do an ugly question live stream. Where that would be cool, because then that would feel much more like when we were doing the Oxbridge prep, when you guys were just like firing me random interview questions. I was just seeing if I could solve them like on the spot. So yeah, that would be really cool to sort of start to bring in. Hopefully that makes sense about like the theory of the gas law stuff that I was trying to describe. Yeah. I don't think there's anything else. So basically though, I think, especially with that, because the kinetic stuff can be really off-putting because the derivation is just pure evil from start to finish. But I think if you just sort of distill it down and go, that's the equation, like what quantities are linked, right? So the average speed of a particle is just determined by temperature. Then you have the link between pressure and density from that equation, plus you have the PV equals a third nm root mean square speed. Diatomic and triatomic gases, bleh. Is that even on the syllabus? I don't know, because I think then you start getting into like, they start to behave non-ideally because they're not perfect spheres, and you start to get intermolecular forces, which violates the ideal gas assumption. I think it gets more complicated than you guys actually get to do at A level. So I would just kind of park that. But if you know your equations, you know you can relate the pressure to the root mean square speed from an atomistic perspective, where you have to know the big N, the number of particles. So this is very much considering it from a particle perspective. Like I said, we know that the average kinetic energy of a particle is 3/2 kT. That's the only thing that affects the average kinetic energy of a particle, and that's the definition of what temperature is. Then I think it kind of makes sense. I think the gas laws then are like much easier to use. I think that's much more intuitive. There's like a change in a situation, the pressure changes. What does that do to the temperature or the volume? Maybe depending on your syllabus, you have a little bit of thermodynamics, work done equals pressure times change in volume. It's not too bad as long as you kind of know how to piece it together, but it can get a little overwhelming because there are just a lot of equations, and knowing which one to use when can kind of be a bit tricky. So just lots of practice. Look at what quantities are given in a question and what equation links them. And then that should help you kind of connect the dots a little bit. Yeah. Could you make a channel? Yes. Although hold on, let me see. Let me in the Discord. I suppose that would be the help channel, actually. Could you make a channel to upload these questions, like diabolical question channel? I thought that was the help channel. So for me, the help channel is like advice or like random evil questions. So you can feel free to start using that, because I don't think it's that sort of populated at the moment. So you can feel free to use that. Or I might just like change the name. Math is kind of better though, but hey, physics can ask some evil questions. Like the AQA Physics 2 for the last few years has just been diabolical. Like student Twitter was blowing up after paper 2. But right. I think in terms of the core theory laying down, if you needed something explained, I think that explained it. Demonstrations, maybe not so much. I tell you what I could do though is I could start doing some multiple choice questions from physics would be good because the mark scheme just gives you the answer but doesn't tell you why the answer is correct, and that would allow me to go through a lot of different topics very quickly and not be writing down, which I think is the most boring part of a live solve. AQA paper 2 is insane. Why don't you do physics paper live solves? I tried it. I found it boring. I was sitting there. I was like, God, this is just so deeply unfun. Like, it was genuinely just because of the writing. And I also think there's less exam technique. So with the math, I think the exam technique is so important. Like the way I check my work, the way I catch my execution errors, that kind of thing. The physics was just, do I know the answers? And I kind of found that boring. And if I find it boring, then what am I doing? Like it won't make it engaging at all for you guys to watch. So, but like, again, maybe as we move through, I'll kind of like, because I think as well, you guys have mark schemes. Like, I don't think the physics is that out of the box, except for the multiple choice. I think maybe doing some multiple choice, like I'll kind of blitz multiple choice, like I'll do the multiple choice from lots of different years in one go as like a sort of big roundup. That could be interesting. I agree. Physics papers are a lot more tedious compared to the math at A level. That's what I find. Like, and you kind of seen now, like you saw what happened when I did the AQA math live solve. I was just booing it the entire time and like, like I want a challenge, which is why I enjoy the EdXL so much. Like I personally find that the most challenging. I also just don't, weirdly, I don't like the OCR where it's just bit by bit. Like I want the EdXL, like it's what I did at A level. It's most of what I teach. So I'm really into like the EdXL format. I have done OCR papers actually. I did a run. I did all of the OCR 2024 papers. At least for the single math. Hold on, let me read back and see if that's what you were talking about. Do you mean OCR papers for the math or for the physics? Because I've done the math run. And one thing I realized I forgot to do entirely, by the way, was going through like the OCR large data set. So I got to this question 11 and I was like, what the hell is this? And I was like, oh, after the fact, someone was like, yeah, it's large data set. OCR physics. Why? Is there a special reason why? Because if so, I'm happy. I'm all ears, but I would kind of need to be convinced because I did not enjoy doing the AQA. And the AQA is the predominant syllabus, I think, when it comes to the physics. So if there's something that OCR does particularly nastily, like maybe I can get in there and kind of see, like show you guys like how I handle that. But if it's just giving you guys answers, that's what mark schemes are for. I think like for my live solves, it's more about exam technique. And I don't think the physics is too bad for that. Mechanics or quantum, the weird comparison ones. Oh my God. I'll tell you what though. That's another reason I really don't want to do physics live solves is I hate particle physics. Like I really hate particle physics. Like I don't want to have to know things. Like I find it very taxing having to know things. And so to have to go into like all the pi z W bosony, no. I like conservation laws, but I have to know those as well. But it just no. I hate particle physics. 6 marks gives me a bait. Yeah, this is the thing about the physics. No one wants to see me write. I think that's why, like, you know, I think it would be more interesting if it was like, hey, like it's sort of an AMA, like, and that's one thing I want to do, by the way, as we move through into the exam season. Like, I'd rather move away from this format where I sort of say, I will talk about this topic and only this topic today. I'd really love to do like a broad revision clinic, AMA, just come in and ask me a bunch of random questions. Because I think especially as we move through to the exams, suddenly you guys are like, okay, I need to know exactly this, exactly now, please help. Everyone's been telling me about this JEE. What is this? Okay, okay. Do you know what? We're having fun. We're chilling. I'm just having some time with the chat now. What is this JEE? Why do I keep on hearing about this? Who sits this? Is this an Indian paper? Because I think this is an Indian paper. I need to find out about this. Why do I keep getting told about this? Yeah, it's an Indian paper. Okay, so JG Advanced. No, I want to see, where are the past papers? I want to see this. Now we're just chatting. Now we're just fully chatting. So let me look at the 2024. Is there only one? It's paper one. How many papers are there? You're saying JEE Advanced papers, they would be very engaging. Let me have a see. I'm just going to scan this real quick. Oh, I'm immediately seeing continuous differentiable equation. I'm like, am I the one? um, oh, some exam technique for the 6 markers. I might have a go. I might dabble. So, okay, tell you what, Edward, why don't you take like a really ugly 6 marker and let me know what year it is so I can track down a mark scheme, because written ones, you really need the mark schemes as well. But we can throw that into a video where it's like, here's how to handle like the ugliest ones. Maybe I do an entire stream where I just do like, here's how to handle 6 markers. It'd be good though to have like specific questions that you want me to go through that you think really get to the core of the problem. So yeah, because I think there are ways to make sure you're walking logically through and hitting all the points, but it does require sort of marks. It's almost like learning how to do like cryptic crosswords, where you have to learn there's a kind of language to it, and you do a few and you look at the answers and then you learn how they want to move, and then the next time you try it, you get a little closer, you pick up some corrections from the mark scheme again, and eventually you just learn like the style of it. Can you explain what we mean by degradation of energy and entropy? No. No, I can't. That is very much not in a syllabus and is very much not something I've learned in a very long time, so I really don't think I'd be good for that right now. So congratulations, you are beyond me. Oh no, I wanted to see about the JEE. The 2016 JEE advanced paper. Well, I'm looking at 2024 and already not enjoying it. Although it is multiple choice, which doesn't seem too bad. Oh no, there's a section 2. Why am I seeing symbols, guys? No, I don't want the symbols. No, why? No, God, this is beyond me. This isn't even fun anymore. Like, why do I need? No, we're getting into the. Does anyone want to watch me just fail a paper? Because like I could do that. Like I did the TMUA. I got 14 out of 20 on TMUA paper 2. The 2016 paper. All right. Do you know what? Just fine. We're having fun. 2016. The physics section 1? Why am I seeing physics section 1? All right, what am I seeing? Why am I seeing a lot of physics? Yes, okay. Physics 2016. Oh, and this has come with solutions though. All right, let me see if I can get one without solutions. No, but now it's different. Oh, I'm immediately like not into this. No. No. Although I am seeing ideal gases, that looks fun. It has negative marking? How does that work? Oh, okay. So if you get it wrong, you lose a mark. So you basically, because it's multiple choice, don't guess. That's not too bad. Oh no. Oh, and it's giving answers for that as well. Yeah, let me put it this way. The JEE would be fun to watch me just flounder, right? Because I think you need to be prepared for your papers. That's why I do the live solves that I do, to demonstrate, oh, when you are doing these math papers, even in between the different boards, there is different exam technique. Like there are different things you need to do to make sure you're ready for this particular paper. Not every paper, if you understand the math and the physics, can you just go in blind and solve it, right? I remember I tried that with like the math Olympiad and the physics Olympiad, and I was like, no, you got to prep for those. And I didn't know that, and I didn't prep, and I did bad. So I imagine the JEE is the same. Like I could get up to speed. Like you saw me with the TMUA go from 14 out of 20 to like 18 out of 20. Like there are improvements you can make. But I think me just going straight in with the JEE, that's beyond me. Like that's not even fun. Like that's, it would be fun if I had trained for it, right? If I had the particular skill set to apply to that paper, but like that would require a lot of training that I'm just not incentivized to put in. Let me see what the chat's saying. Imagine going as a student to write that. No, that'd be awful. But like, I know if I was a student, let me put it this way. Me as a student, was objectively better than I am now at taking exams. Like, the first time I lost a mark in physics, I was at university. Like, I was very, very well trained, very good. I knew every word of the textbook. Like, I could do the papers. Now I'll make mistakes because I'm like, that's kind of not, I'm retired from that game now. Like, I still do the teaching of it, but like, I'm not really in the arena in the same way that I was before. I imagine if you're a student, like sort of really drilling for that one particular thing for ages, I imagine you feel much more ready for it. Yeah, the escape velocity. I remember that the escape velocity, was it the escape velocity of hydrogen? Like, why there's no helium? Why there's no helium? Because the remembering that the temperature at the surface of the Earth determines the average kinetic energy. That determines the CRMS. Then the root mean squared speed would be sufficient for it to reach escape velocity and escape the atmosphere. I remember that. Am I a school teacher or a tutor? Very much a tutor. Like, this is no. I'm not professional enough to be a teacher. I don't want to do the classroom management. I don't want to do the planning. I don't want to do the marking. I don't want to do the waking up. I like, you are everyone. Why? Okay. Like, I can't look that much like Daniel Radcliffe that I've got this level of comparison since I was 10. I can't look that much like him. Like, I know I look like generic white actor number 7, but like, I can't, we don't look that alike, in my opinion. Okie dokie. So I will see you guys hopefully tomorrow. So in the meantime, take care. Hope you enjoyed the gas laws, and feel free to keep popping things in the Discord if you want me to cover them on stream. Right, brilliant. Thank you very much, guys. Take care. See you next time. Bye-bye.